Good morning, dear students. Welcome back to the subject of network analysis. In this video, we are going to learn about Laplace transformation. So, what is Laplace transformation? That is, Laplace transformation. This is actually the solution of any physical problem can be obtained by time domain analysis or by frequency domain analysis or approach. That is conversion of time domain function to corresponding frequency domain function is known as transformation. Is known as the transformation. It is known as the transformation. And the reverse process is called the inverse transformation. From Ft to Fs, it is called transformation, and from Fs to Ft is called inverse transformation. This is point number 1, this is point number 2, this is point number 3. What I have told you that the transformation of any system or simply a function in time domain to frequency domain is called transformation. The tool which is used to transform is called, it is used here, is Laplace transformation. Now the point is, what is actually Laplace transform? What is actually Laplace transform? Let us learn this. Laplace transform of any time domain function, Laplace transform of any time domain function ft is given by Fs when S is complex frequency, where S is your complex frequency. Mathematically, it is given as Laplace of function ft, which is equal to f of s. Now the f of s is equal to integral from 0 to infinity of the function ft into e raised to power minus st dt. This is the formula for Laplace transformation. Just see this. The time domain function, this is your time domain function ft, is converted to frequency domain function f of s by applying the tool L. L is written like here. And the formula, the mathematical formula is f of s is equal to integral from 0 to infinity ft. Ft is your given function. Ft is your time domain function. This is nothing new. This is the time domain functions at your hand. This was given initially. Integral from 0 to infinity ft e raised to power minus st dt. Okay, let us understand. And the time domain function ft can be obtained by inverse Laplace of the frequency domain function fs. What does it mean? It means if you have converted f of t into f of s, so at the end you are having f of s. Now suppose you want back your system from f of s to f of t. So this is called, this process of getting back your signal from frequency domain system to time domain function or time domain system is called inverse Laplace transformation. But it means what? You are inversing the Laplace transformation. First, at the first hand, the Laplace transformation was done, the Laplace transform was done to convert or to transform time domain function into frequency domain function. Now, if again from frequency domain function to time domain functions, if you want to get from frequency domain to time domain, it is actually inverse of the transformation, inverse of the Laplace transformation. That is called inverse transformation. How it is done mathematically? How it is done mathematically? The question is like this. The question is, the formula for f of t is equal to L inverse of f of s. That is, formula is 1 by 2 pi j integral from sigma minus j infinity to sigma plus j infinity of the frequency domain function fs into e raised to power st ds. This is your inverse transformation from this to this. This is your inverse Laplace transformation. And this notation is called inverse Laplace transformation. Okay, let us move towards to understand the advantages of Laplace transformation. This is very important, dear students. There are certain very peculiar advantages of Laplace transforms which we must understand. Advantage number 1. Let us understand this is here. Advantage number 1. We are going to understand advantages. Advantages of Laplace transformation. Just listen it very carefully. The first point is the transform converts the time domain integral differential equation into an algebraic equation. That is, it converts ft into fs. And this is having some sort of d by dt form and integral, that is called integral differential. The time domain integral differential equation is converted into frequency domain system, and this frequency domain system is some sort of algebraic kind of system, which is very easy to solve as compared to time domain integral differential system. This was called integral differential system. This is some properties. We'll understand this later on. Just first, let us move towards the next slide to understand that the first hand, this is your time domain integral differential equations. I'm just showing it by notation. It is converted into f of s, and it is very much easy to solve. First point. Second point is that Laplace transforms makes the solution easy and less time consuming. Of course, if it is algebraic kind of system, if it is algebraic, the algebraic equation requires less time to solve as comparison to this integral differential time domain system. If you are having a differential equations having lot of differential parameter, lots of integral parameter, so it will require more time to solve as comparison to frequency domain, which is algebraic equation. Algebraic equation requires very less time to solve as comparison to your integral differential calculus equation. Point number 3, advantage. That was in time domain analysis. That is, if the system is ft and we are also performing in the time domain system, one have to find the complementary functions and the particular integral for the complete solutions. That is, you have to find for complementary functions. You have to find complementary functions and particular integral, pi, particular integral for the complete solution. For the complete solution, it is required to find complementary functions and particular integral for the complete solutions. So there is another approach to observe that time domain integral differential equation requires more time and more skill, and it is actually very laborious to solve. Though it is giving you solution, but it is having a requirement of giving more time and more skill to solve as comparison to your frequency domain system, which is actually algebraic system, which is very easy to solve. Initial conditions are automatically considered in Laplace transform operations. Point number 4, which is very important. Let it make it a star 1. The initial conditions are automatically considered. Initial conditions in Laplace transforms are automatically considered. That is, it is the beauty of Laplace transformation. Automatically included, automatically considered. So it is very important to understand this. Let us understand one by one Laplace transformation of some important functions. I am going to solve for you a very fundamental Laplace transformation for you, that is under the heading Laplace transform of some important functions. This is the heading of, we are going to have some important functions transformed by using Laplace tool, L. This is L tool, Laplace tool. First one is your exponential functions. That is, f of t will be equal to e raised to power minus a t. So f of s can be written as So if f of t is equal to e raised to power minus at, so Laplace transformation which is represented by f of s is equal to that is integral from 0 to infinity f of t e raised to power minus st dt is equal to integral from 0 to infinity e raised to power minus at. Put the function, put the value of ft here, so e raised to power minus at into e raised to power minus st dt, that is equal to, that implies integral from 0 to infinity e raised to power minus, take common, minus s plus a into t dt. So the value of integral of entire this thing will be equal to 1 upon s plus a. Okay, call this equation number 1. Call this equation number 1. F of t is equal to e raised to power minus at. So f of s of ft, here it is 1 by s plus a. Now see this, compare this. Ft was e raised to power minus at, and fs is the same functions, the same time domain functions converted into frequency domain function via tool, via mathematics, Laplace transformation here, which is very easy to see. Look this, 1 by s plus a, it is basically algebra. So consider this for a bigger system which is a heavier in time domain and differential equations having lots of integral also. If that is converted into this kind of algebraic equation, that requires very less time to solve. Okay, let us have some corollary. Similarly we can have integral of k into e raised to power minus at will be equal to Laplace of k into e raised to power minus at will be equal to, k is constant, k upon s plus a, and Laplace of e raised to power at will be equal to 1 upon s minus a, or Laplace of k into e raised to power at will be equal to k upon s minus a. Now put a is equal to 0 in equation number 1. What we'll get? We will get equation number 1. We are having ft is equal to e raised to power minus at. Now a is equal to 0, so it will be f of t is equal to e raised to power 0 is equal to anything raised to power 0 is your 1. So if f of t is 1, so what will happen? If f of t is 1, so what will happen? That is 1 by s. The Laplace of f of t is 1 by s. That is Laplace of is equal to f of s is equal to 1 by s here, where ft is your this. Now point number 3, put a is equal to minus 1. Put a is equal to minus 1 in equation 1. What we will get? We will get, just see, equation 1 was your ft is equal to e raised to power minus at. If a is put minus 1, it will be like put a is equal to minus 1, it will be like, then this was your equation number 1, equation 1. So f of t now will be equal to e raised to power t, e raised to power t. So integral of, Laplace of f of t will be equal to fs is equal to 1 by s minus 1, 1 by s minus 1, isn't it? So initially it was, when it was e raised to power minus at, the Laplace was coming 1 by s plus a, 1 by s plus a. When we put a is equal to minus 1, the Laplace becomes 1 by s minus 1, 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 and the function becomes e raised to power t. How it becomes e raised to power t? By putting a is equal to minus 1. Just put this thing into this. So minus of minus will become plus, and plus 1 into t is actually et, and this is your Laplace of these functions. Laplace of these functions. In general, what we are going to write, Laplace of t raised to power n, is equal to factorial n upon s raised to power n plus 1 plus 1. In general formula, this is the Laplace of t raised to power n is equal to factorial n upon s raised to power n plus 1. Now let us move towards another thing. Now put a is equal to j omega in equation 1. It will become f of t is equal to e raised to power minus at is equal to e raised to power minus j omega t. So the Laplace of f of t will be equal to 1 by s plus j omega, In the place of a, we just write j omega. Now by Euler's theorem, we know that e raised to power minus j omega t, e raised to power minus j omega t is actually equal to cos of omega t minus j sin omega t. That is, therefore Laplace of cos omega t minus j sin omega t equal to s minus j omega upon s square plus omega square. This can also be written as in Laplace of cos omega t minus j sin omega t is equal to, expand this s upon s square plus omega square minus j of omega upon s square plus omega square. Now just compare the real part and imaginary part of both the sides. Compare real and imaginary part both sides. What we will get? We will get Laplace of cos omega t is equal to s upon s square plus omega square, and Laplace of sin omega t is equal to omega upon s square plus omega square. So this one is your another formula separately for cosine term and sine term. From this one you can write like this. Now put a is equal to, what we have to do? We have to do put a is equal to plus sigma plus j omega in equation number 1. So equation number 1 will become ft is equal to e raised to power minus sigma t minus j omega t. So let us understand how to calculate the Laplace transform of this function, which is f of t is equal to e raised to power minus sigma t minus j omega t. So it will be like in general it can be written as Laplace of f of t is equal to Laplace fs, which is equal to here 1 by s plus sigma plus j omega.